Uh, just before the intermission, I talked to you about where I have systems where which need to be functionalized. Now, let me take specific examples where I would say extrusion, where clay is not used. Let's take graphite. Let's say I want a graphite powders to be mixed, then they be extruded in the form of rods or tubes. What would be the additive? That is the polymer. I would add here 50 to 60 parts phenol formaldehyde would be my base additive, because when I have extruded it, I can burn this phenyl formaldehyde off, which will leave a lot more carbon, and this carbon will be really in the submicron range. I would rather say in the nanometer, 5 to 10 nanometer range, which would aid in sintering of the graphite grains which I have started with. Normally, in extrusion, the finer the grains, the better is the extrusion. And normally we use 1 micron sized or less powder of the basic matrix. Let's see if I am going to have silicon carbide. I want to make silicon carbide tubes. What would I do? I would take say 30% silicon plus 70% silicon carbide powders mixed, and here my additive would be say about 4% guar gum, 20% water and 3% silicone. These are weight percent. So, I have got 20, 24, 27 weight percent of this, and hence this will be overall 73 weight percent. Each of these are going to functionalize the silicon carbide and the silicon. And what would they do? The silicon would react with the carbon generated from the silicone, from the guar gum, form silicon carbide and aid in sintering of the silicon carbide grains to give us the silicon carbide tubes. If I am going to make, say, you make a magnesia tube, MgO, which is very important in high power thermionic tubes. I guess those you have not seen, but those formed the base of entire communications industry before the advent of the transistors, and today these thermionic tubes are really at the heart of millimeter wave or long wave communication. So, we need magnesia rods, we need magnesia tubes. What would be my additive here? It would be flour paste. One of the best things that is available for dispersing the magnesia. Both will have hydroxide. MgO will react with water to give you magnesium hydroxide, which when heated will give you back magnesia. So, there will be reactive sintering. The flour paste gives you the much needed dough, like the dough you have at home when you make chapatis, and these are used for making very high power vacuum tube parts. Now, if I want to extrude a refractory rod or a brick made up of alumina, what would I have? I would have alumina as a ceramic, hydroxy ethyl cellulose as the binder, water, and a small amount of aluminum chloride, which helps the dispersion of alumina in this matrix. If I want to have an electrical porcelain, what would I do? Electrical porcelain. My constituents would be quartz, 16% weight by SO, feldspar, kaolin. Now this is clay based, ball clay, water, and calcium chloride, which aids in dispersion. We can use various combinations. You can see here, I have taken merely the raw materials. So, when say this is extruded in the form of a rod, all these raw materials will be dispersed, all of them, the quartz, the feldspar, the kaolin, the ball clay, all of them will be dispersed. This by itself is not the electrical porcelain. This has to be fired so that all these materials react with each other to give the electrical porcelain. So, this is firing for what? A binder burn off, B reaction sintering. This is what I had talked of earlier in my last class. Here I am talking of huge reduction in size, and hence the compaction, everything has to be very, very well controlled. Without it, you will get shapes of different sizes depending on the batch, which will be unacceptable. You see, to make such a homogeneous thing, we require very, very high level of mixing, and mixing is a critical step in the operation of this extrusion. Let me say something that I used to do. When I was a kid, I was very naughty. So, when my mother slept, I would go into the kitchen and the storeroom. I would find out the honey pot of honey, take extra sugar, try to mix it. For those of you who have tried to do this, you would have seen that mixing these two to get a uniform consistency is very, very difficult. It's not the size of sugar. I took very fine sugar, yet I never could mix it. I would have pockets of honey, pockets of sugar, but never a uniform one. Why? Because I was not using enough force to stir and cause the mixing of the honey and the sugar. So, whenever I talked of say magnesia and flour paste, I said to make magnesia tube, it requires tremendous brute force to mix it. In fact, though your mother kneads the dough, if you just imagine how much pressure she pushes on the dough when she is kneading it, is a huge pressure. Now, she is using her palm. You have seen how close the blades of the twin screw extruder are, how thin. They have to be very close, thin enough so as not to buckle. So, the twin screw extruder design has to be such that as the screws rotate counterclockwise, the force with which you knead the dough at your home to make chapatis is available to the matrix. Otherwise, mixing will never happen. So, that is what the pug mill was all about, where they mix it. Now, what is it that is required? As I apply the brute force, do I want the shear action to force the viscosity to go down? Is that what I want? Say I take the MgO and the flour paste. I do not add the full amount of water first. I just force them to mix, add the requisite water slowly, just as your mother does while kneading the dough. But then at the initial stage, when the flour is dry, your mother has to apply huge pressure. Do I do that? That is, add water in incremental steps, so that as mixing occurs, as hydrolysis of flour paste occurs, the mixing improves? Or do I add the full amount of water first and then mix it? The problem is, if I add the full amount of water first, mixing would never be uniform. So, viscosity is not the key parameter. The real factor is the mixture must have the proper property when the force is applied. The preferred type of flow is shear thinning, or it is also called Bingham flow. It means as you apply more and more shear, the material starts flowing. What are the different types? Before I explain what is Bingham, let me draw a diagram. This is, let us say, apparent viscosity, and this is, let us say, the shear rate. Now, a Newtonian flow is this, that is, slope is 0. In Bingham plastic, this is what shear thinning is. This is what shear thinning is. The other one which we often encounter is dilatant. That is, as the shear rate increases, the viscosity increases. So, during mixing, the preferred type of flow that we require is shear thinning. However, we do not want pseudoplastic. Where do you see pseudoplastic flow? When in the morning you wake up, you go to brush your teeth, you press the tube, the paste comes out in cylindrical form and stays that way. So, what happened? The paste under pressure got squeezed out in the form of a rod, and that you took on your toothpaste. That is pseudoplastic. When a potter makes anything, when the wheel is spinning and he is molding the whole thing with his hands, that is pseudoplastic. This flow is certainly what we don't want. We want shear thinning, so that if you remember the first slide where they showed how the distance between the blades and the surface decreases, the viscosity falls, that is shear thinning. That is very, very, very desirable. Secondly, the most important part is die design. I had shown you that diagram where they are extruding ceramic pipes. Now, you see, by injection molding, by extrusion, we can have honeycomb structures. These are the open spaces and these are the ceramic bodies. Today's extrusion level has reached, extrusion process reached such levels that a complex honeycomb structure like this is easily fabricable. Many of these structures can be fabricated. This easily fabricated today. So, in these cases, to have absolute uniform porosity, the die design is very, very crucial. It's the die design, the die has to be smooth. The design, for example, it has gone away, maybe I can bring it back here. Forget it, I lost it. Where you saw that the spruce is over here, the die wall is here and the material is flowing right across this without collapsing. It does not collapse, it just follows right across, giving us the tube. So, here this angle of the die, this angle, because the flow is being diverted in these two directions, they without causing any turbulence, because any turbulence at this point would cause defects over here. So, the die design, the smoothness of the die is of paramount importance. It is beyond the range of this course to talk of the die design, the considerations, but other than the flow characteristic, the die design is another very important parameter in ceramic extrusion. The third aspect is there is a significant amount of liquid or polymer in the green body. So, as I had said, burn off has to be A, controlled, B, reproducible. And hence, the burn off times have to be fixed. Here, this is dependent on particle packing, this is dependent on particle packing, thickness, at least these two. So, one must have very rigorous quality control over these two things. If this issue, flow characteristic, die design, burn off, if these two are not taken care of very well, what we will land up with is extrusion defects. First of all, as I said, one diagram I drew, that is, I have this whole material which has got 80 volume percent polymer. Unless I have reproducible properties, I will face, after burn off, various shapes. So, warpage is a problem which has to be avoided at all costs. Warpage is a problem after firing, and also it can be after extrusion itself. I have not even gone into firing. This can all happen if the mixing is not very well. The second problem is lamination. Well, if I look at the cross section of a extruded rod, what I will see, and if the screw was turning in this direction, what I will see is there are zones where the polymer and the ceramic has separated off, and they are showing this type of a defect. This is if I see it in plan. If I look at the side view, what it would look like is, if this is the extruded body, it would very well look like as if the polymer and the ceramic, they have separated out. This happens if the plastic mix is not very well done in the hosier. Unless it is very well mixed, we will have lamination as a problem. The third one is tearing. Because the extruded material comes out of a barrel, what may happen is when it comes out, due to friction, it may show tearing at the surface. Because the molten polymer is flowing past the spinneret, it is cooling, there is adhesion between the die wall and the polymer is cooling down, tearing may very well occur. The fourth one is segregation. This is different from lamination. Here what happened, the polymer, ceramic, they were mixing, but the hosier did not mix it very well. The stress given was not uniform, so we got this sort of structures. But in segregation, here the liquid and solid separate out. This results in cracking, distortions, and in fact rejection of the piece. The piece is no good. Now, these are basically, all these defects are what we call macro defects. But what we fear the most in extrusion are micro defects, like bubbles, trapped, microscopic bubbles, powder, agglomerates, binders can also agglomerate, and so on and so forth. Whatever we are using for mixing up. While ceramic extrusion, as I have said, is now an industry standard process, you have seen single screw extruders, double screw extruders, honeycomb structures I showed you of ceramics made by extrusion process. So the technology has developed, it has surmounted the barriers that had plagued it, but yet one has to be very careful as to how each of the process steps are implemented. Mixing, ejection, die design, all of them have to be taken into consideration, to say the least. I would now move into the next one, injection molding. Big name. The bucket that you use in your bathroom has been made by injection molding. Most of the plastic plates that you see have been made by injection molding. Most of the plastic containers, say your glasses, toys, they are made by injection molding. Not far from here is a place called Bagnan, about 80 kilometers away or 70 kilometers away. There are small rooms of the size of 10 feet by 10 feet where people use injection molding machines for fabricating toys, pipes even, and it does not, it's today not really limited to heavy industries. Where people fabricate pipes, toys even from 10 feet by houses where they put their own injection molding machine. They bring the polymers, purchase it from China, elsewhere, have the injection molding machine at their house and make toys, pipes, anything they want. So this is not something that is out of this world. It has become now what they call is small scale industry. Now before I go on, like in case of extrusion, let me show you how an injection molding machine works. Because the problems that I had talked of during extrusion are there in injection molding and lot more. So first, let us get a good feel as to how an injection molding machine works.
Resin material is fed to the injection barrel from the hopper. These hoppers may be filled manually or vacuum fed automatically, and often have dryers attached to the top to remove the moisture from the material. As the resin enters the injection barrel, it is driven forward by the rotation of the screw, which is powered by the hydraulic motor. The resin plasticizes or melts as the turning screw drags it towards the nozzle end. This is referred to as drag flow. Drag flow causes the polymer molecules to slide over each other, creating frictional heat, which melts the material. External heating bands provide additional heat to the injection barrel. The heating bands bring the material to its final temperature and compensate for the radiation heat loss. The temperature is controlled by 3 thermocouples in the barrel and 1 in the nozzle.
well. That was the first part of how an injection molding machine works, which is almost not different from the extrusion one. Now, let us look at the second one. Here what is happening is, this is, look at the thing that is going to be injection molded. This part. So, the liquid has come, again the die moves in, it is filled by the liquid from the injection molding machine, it goes on to fill it, then the ejector pins force the die apart and the part falls off. Basically, this is how injection molding is done. Let me take the last one. Here, the difference is, you will see they will put a bit of spacer out here to increase the thickness. In the previous one, if I go back to the previous one, we have always had a problem. Here you can see the gap which is open. So, what happens is, if you will notice, it is now closed over here. So, the thickness is really controlled by what is the distance between this part of the mold and this part of the mold. Over here, just watch how the distance is matched. They bring a spacer in here so that this distance is covered. So, the thickness, depending on the spacer, the same machine can be used to make thicker or thinner plates. Whereas, in this one, I would have to change the entire die design. That is one problem I have with such machines. And if we are ever going to make such a complex rotor by injection molding, this is the silicon nitride rotor which is to be used in space. The thickness of the blades are varying depending on what the angle is. The shaft here is thinner than the end, and there is a constant variation of the thickness. So, such complex designs for use for injection molding, which is possible, but then one has to decide on the die design all over again. Anyway, so let us carry on with injection molding. Basically, you may say, hey, injection molding is same as extrusion, because I am melting the polymer is mixing with the ceramic, that is how the blades are moving, and there is fundamentally no difference. The difference is in injection molding, we use only a thermoplastic polymer. Along with a plasticizer and anti-foaming agent. This is essentially different than extrusion further, because if you remember the barrel where it is heated, do I have a diagram? I guess I don't. But the barrel is heated. The polymer has to melt. It can jolly well form bubbles. This anti-foaming agent is basically very essential to avoid defects in injection molded materials. Secondly, if you go back over my lecture, you will see that the nozzle through which the injection molded material came out, it was much more finer than in extrusion process. And because the material is heavily loaded with ceramic, the flow can become very, very irregular. And hence, to avoid it, in injection molding, the viscosity has to be much lesser, much lesser than in extrusion. Most why? You see, what is happening in injection molding? To draw a very simplistic diagram, let us say this is the mold into which the injectable material goes in. What can happen over here? One is, as it goes in, it may not fill the mold. The flow lines may not be uniform, and so we can have mold filling defects. Most importantly, if a mold which appears to have filled and then it solidifies, volume shrinkage occurs. There will be a lot of solidification defect. There will be a lot of solidification defect. Now these, the mold filling defect, the solidification defect can be seen, but the question comes, how do we avoid it? One of the ways is to ensure that in a mold, as it fills up, filling up is uniform. This, however, is entirely dependent on the viscosity of the injectable material and the way the material moves in this. Let us say, let me take this diagram again. Basically, to have this rotor made, what did they have to do? They had blanks where this was empty space in the mold, very thin. The liquid may have show turbulence as it flows in. If I increase the temperature, decrease the viscosity, the flow characteristics might totally change, and hence for such complex shapes, defects are very, very common. Secondly, as I said, look at the thin. This one is hardly 1 millimeter. This one is around 10 millimeter, and this is about 30 millimeter. If this is injection molded, then the first question comes, from which side was it molded? From this side or from this side? If I leave it to you, I guess you will turn up with the wrong answer. It was filled up from this side, so that the thicker parts got filled up first, then the thinner parts as it came along. In this complex geometry, having a defect-free casting requires tremendous control on the viscosity of the liquid. The injection pressure, the force at which you are injecting the liquid, the hold time, the time you are holding the material in the mold, temperature, which controls viscosity. A lot of these factors have to be taken into consideration before this rotor can be fabricated perfectly. Surface flaws are also obvious, because here I have got finer nozzles, higher flow rates, and hence surface flaws are a possibility. The next important problem that we have is, this was about mold filling itself. Because of the complexity of the design, the thinness of the spaces, would the liquid flow all uniformly through the mold? But let us presume that the liquid has flown, the mold has filled properly. Then comes the solidification problem. You see, these are hardly 1 millimeter apart, these blades. But this is 30 millimeter, 3 centimeter. This is 10 millimeter, 1 centimeter. So, as a result, when the liquid is, or when the mix is solidifying in the mold, the rate of heat transfer would be faster in the blades, then it would be over here, and in this thick part, it would take a long time for it to solidify, because of the very fact that this whole thing has been made in one go. This is very thin, so it would cool down fastest. The next one would be this shaft, and this end part would cool down the slowest. This variation in solidification rate causes a lot of gradient change, a lot of packing fraction change in the whole body. In fact, it is known to cause voids also due to differential cooling rates. Add to it my problem of everything that I talked of in extrusion, binder, burnout, or prior to that drying, binder burnout, shrinkage, all the problems that I discussed during extrusion are equally applicable over here. In fact, it is a worse state. In extrusion, you had a uniform cross section, if you remember. It was either a pipe or a rod or a brick or something. It was uniform. Here, you have got varying cross sections. And injection molding is a real tough one for fabrication of ceramics. Though I must admit, it is a proven industrial process. Materials are already available in the market and are being used in space, like the turbine rotor I had shown you. And but what has happened is, in injection molding of ceramics, it is technology specific. You can have lot of extruded ceramic bodies, honeycombs, pipes, anything. In injection molding, due to the limitations I had said, it is technology specific, and the mold costs are very, very high, just awesomely high. The dies are expensive. In fact, injection molding is a very, very expensive process as opposed to extrusion. I guess I shall stop over there with injection molding and take it off in the next class.